Dear colleagues, our today's lecture is about bottom-up parsing and how to apply and construct a simple LR parser. First, I'm going to introduce the basics of bottom-up parsing, how to implement it by a pushdown automata, how to apply a parsing table, a bottom-up parsing table, and how to construct a bottom-up parsing table. The examples are from the book Compilers by Aulem, Sethi, and Ullman. Okay, so the basic idea is that we are going to construct the parse tree from the leaves to the root, applying the derivation rules backwards, so replacing the right-hand side of the rule with the non-terminal on the left-hand side, until reaching the star symbol. So, for example, if we have these three non-terminals and four derivation rules, and we are going to check whether a sequence of symbols can be derivated by these rules. First, we are going to identify a sequence of tokens for which it is easy to find how it was derivated. So what grammar rule resulted it. For example, if we have a standalone B somewhere, then it can be derived from a non-terminal A, and applying it backward, we can replace the B by a capital A representing the non-terminal. If we have a sequence like ABC, it can be derived from the non-terminal A again, so it can be replaced backward by the non-terminal A. And here we have a sequence of A, capital A, D, and F, where D can only be derived from non-terminal B, and backward it is replaced by non-terminal B. And finally, we have a sequence A, B, B, F, which can be derived from the initial symbol, from the start symbol. So as a result, we could go back to the start symbol and from the sequence of tokens. Okay, such a pattern, which can be identified and helps us finding a derivation rule, is called handle. So we are looking for handles, and based on them, we are going to identify the derivation rules to be applied backward. If the derivation rule is applied backward, it is called reduction, since typically on the right-hand side of a derivation rule there are multiple symbols, and if we replace it by a single non-terminal on the left-hand side, then the sequence of symbols becomes shorter. Okay, for example, if we take a look at this example where we have derivation rules like e to e plus e, e to e multiplied by e, and e in braces, or e to id, then if we have a sequence of tokens like id plus id multiplied by id, and the id can be a handle because it can be derivated from non-terminal e, so we can replace the id by an e, and the reduction rule is e to id. Similarly, in the second step, another id can be replaced by a non-terminal e, and finally the third id can be replaced by a non-terminal e. As you can see, in the third step, it is not easy to decide whether we should reduce by e to id or by e to e plus e, because we have the opportunity for both. And here we have e plus e multiplied by e, where we could reduce by e plus c or by e multiplied by e. Let's see the second case, where E multiplied by E is reduced to a single E, and then E plus E is reduced to E. As you can see, sometimes we have to take into account more than one symbol from the input, and sometimes it is not easy to decide which of the derivation rule is to be applied. In the case of bottom-up parsing, we have altogether 4 potential actions. Shift means that we are going to move a symbol from the input to the stack. So the input is read, the reading head is positioned to the next place, and the symbol read is placed to the top of the stack. Reduction means, as I mentioned, that we apply a rule backward, which means that the right-hand side of the rule is replaced by the non-terminal on the left-hand side. And finally, we have 2 terminal actions. Accept means that we have accepted the whole input, which results that which expresses that all the input sequence of tokens is acceptable, so it can be generated by the grammar, which defines, for example, the syntax of a language. And the other terminal action is raising an error message when we raise that the sequence of tokens cannot be generated by the grammar defining the syntax of the input. And as I mentioned at the previous slide, we can have multiple dilemmas during executing such an algorithm. For example, whether we should take into account more symbols from the input or reduce by the reduce the sequence already in the stack. It is called shift reduce dilemma, since the shift is the operation where one or more symbols from the input is moved to the stack. And reduction is when we apply grammar rule backward to the symbols at the top of the stack. So when we are going to apply a reduction, it is expected that the right-hand side of a rule can be identified at the top of the stack. And the dilemma is whether we reduce by the sequence of symbols already in the stack or add additional runs from the inputs. It is called the shift-reduce dilemma. And the other is the reduce-reduce dilemma, when we are not sure which rule is to be applied. For example, going back to the previous example, if we have the input id plus id multiplied by id, first we have to shift because the stack is empty. The bottom of the stack is often identified by a dollar mark at the bottom. So if we see only the dollar sign, then it means that the stack is empty. So we are going to shift the first token from the input, which is an ID, and it can be reduced immediately to a non-terminal E by the derivation rule E to ID. Then we can shift and add the plus sign to the stack, but E plus cannot be reduced. So we add an additional symbol where we have E plus ID as a result of the next shift. And it cannot be reduced either. So we can reduce the ID to have an E at the top of the stack, and altogether E plus E in the stack, which could be reduced. But in this case, we are going to go further, and based on the input with the multiplication sign, we decide to go further and place the $sign at the top of the stack and then the ID by 2 consecutive shift operations. And then the third ID is reduced to be an E non-terminal, then E multiplied by E is reduced to E, and finally E plus E is reduced to B and E. And this is the initial symbol, and we could produce it by applying derivation rules backward from the input sequence of symbols, which means that the input sequence can be derived by a sequence of derivation rules from the initial symbol, and we do not do anything else but applying the reduction rules in the reverse order. So first apply E plus C, then E multiplied by E, then E to ID, E to ID, E to ID, and we get this sequence of symbols, which is actually at this point at the input, and what we wanted to generate by the grammar rules. So at this point, we can be sure that the input sequence of tokens can be generated by the derivation rules, and that's why it can be derived by the grammar rules in the grammar, and that's why it meets the requirements for the syntax, and that's why it is accepted. How such a parser can be implemented by a pushdown automata? Actually, it is typical that different classes of languages, we have different parsing algorithms and some kind of definition of specific grammars. For example, for LR parsers, we can have a LR parser algorithm, and in the definition of the grammar, we have two tables. One is the action table and the other is the step table, as you will see later on. And we have the input with the $sign at the end, and we have a stack where we can store not only tokens but also states, as you will see later on. So this stack is going to store not only the symbols pushed from the input, but also some information on the other symbols below in the stack in the form of a state of this pushdown automata. And as you could see from the LLK languages where we had a general derivation algorithm and we had a parsing table for a specific grammar, the situation is similar here. So as you will see, for simple LL parsers we have a single algorithm, but for all the grammars we will have different action and step tables defining the specific grammar. Okay, if we have a certain configuration of a pushdown automata which involves the stack and the ended part of the input, and as I mentioned, the stack contains not only symbols from the input but also states, and at the top of the stack we have the actual state. So this content is to be read from the bottom to the top. So the first state is the initial state and the last one is the actual state. And if we apply a shift operation, it has two parameters. One is to define that the operation is shifted, not a reduce, and not an accept and an error. And the second parameter is the forthcoming state. So for example, if you have a shift S operation, it means that we are going to move the first symbol AI from the beginning of the input to the top of the stack, and here we have a new state which is going to be S. So shift S means that we are going to place an input symbol from the beginning of the input to the top of the stack, and we are going to add the actual state to be S. If we are going to apply a reduction, so we have in the action table not a shift operation but a reduce operation. As you will see, this table has two input parameters, one specifying the rows, another the columns. The rows the rows are assigned to the actual state and columns to the potential input symbols. So the next operation is selected based on the actual state, which is actually at the top of the stack, and the next input symbol at the beginning of the input. So if this action table specifies that the next action to be applied is a reduction by a rule from non-terminal A to a sequence of symbols W, and this sequence has a length of R, then we are going to remove the R topmost symbol together with the corresponding states from the stack. So practically the symbols and states down to the symbol M minus R and S minus R are removed. And instead we place the left hand side of the rule, so is placed at the top, and the actual state is generated by applying the step table, where we take into account the top of the stack, including the state just below the non-terminal, and also the non-terminal we just placed at the top of the stack as a result of the reduction. So we remove a sequence of symbols from the stack, place the non-terminal on the left-hand side instead, take a look at what state is below it, and we are going to determine the next state as a function of the state below the non-terminal and also what the non-terminal is. And in this case, the unread part of the input remains the same as it was. And finally, if the action table at the actual position based on the actual state and the forthcoming input symbol contains an accept operation, then we are going to accept the whole input. If it contains an error, we are going to initiate an error recovery method. Okay. As I mentioned, the parsing table consists of two parts, actions and steps. So the action table and the step table. As you could see at the previous slide, the action table specifies what is the next operation based on the actual state and the forthcoming input, and these actions can be shift, reduce, accept, and error. And the steps specify the next state when a reduction is applied, and we have to take into account what is the non-terminal at the top of the stack and what is the state below. Okay, and finally we can have two kinds of outcomes when whether if the W word at the input is an element of the language defined by the grammar, then this parsing algorithm results a parse tree, otherwise it results an error message. First, we have to place the initial state to the bottom of the stack and run the algorithm until it reaches an action accept or error. Let's see an example. If we have a grammar like e to e plus t, e to t multiplied by f, t to f, and f to e in braces and f to id, then how such an LR parser can be constructed. As you can see, these grammar rules includes some with left recursion, but it is not a problem for LR parsers in contrast to the LLK parsers, where we had to modify the grammar not to include left recursion. Here it does not cause any problem, so we can use the original definition of the grammar, including the left recursion. Okay, so the parsing table looks like this. The rows are assigned to the states, the columns to the potential input symbols, and we have the step table where the non-terminals are listed in the columns, and as I mentioned, we are going to take into account the states just below the non-terminals at the top of the stacks after a reduction. SI means a shift operation where the next state will be state I. RJ is a reduction by a grammar rule where J is the number identifying the rule. So for example, if we have R6, we are going to reduce bar F to I by the rule F to ID. So practically we are going to remove ID and place an F instead. So in this case, it is when we have a symbol right after the ID. For example, we have a multiplication sign or an addition, or we close a brace, or we reach the end of the input, because the ID can be just before the addition, multiplication, or it can be at the end of the input as well. ACC means the accept. So in state number 1, which is reached when we reduce to non-terminal E, and we have a state 0 below, so nothing else is in the stack but the initial state and the E. So we have reached the initial symbol. Then we move to the state I, and in this case, if the input ends, then the input is accepted. And finally, to each empty cell, we are going to assign an error message. Okay, how to create such a parsing table? First, we introduced the LR0 items, which are practically the grammar rules, including dots. LR0 item looks like a grammar rule, but in the right-hand side there is a dot, and exactly one dot. And this dot specified the position of the processing. So for example, if the dot is just below an X, we expect that at the beginning of the input there is something which can be derived from X, Y, Z. If it is after the X, we assume that we already have read something can be derived from X, and the remaining part of the input is expected to be derivable from Y, Z. And if the dot is after X, Y, then probably we already have read something which could be derived from X and Y, and the remaining part can be derived from Z. And finally, if we have a dot at the end of a derivation rule, we expect that we have already read something which could be derived from x, y, z, and what is the forthcoming symbol and the input is not derived from this non-terminal A, but something which can follow those symbols can be derived from A. Okay. There is also a term called closure, which means that we extend a set of R0 items in a way that, for example, if the dot is just below a before a non-terminal, and we have a certain rule for this non-terminal, then the dot can be at the beginning of something which can be derived from this non-terminal. So if we are just before a non-terminal, then it means that we are just before applying something which can be derived from this non-terminal. And such a rule should be applied as many times as it could, and we can stop only when this set cannot be extended further. So any such a application of derivation rules does not lead an additional rule not in the closure already, then we can stop, otherwise we have to continue this extension. Okay, let's see our example where we have, for example, these rules that we have e prime to e, and then e to e plus t or t to t multiplied by f or f, and f to e in braces or id. And let's see, this first one is an artificial rule added to the grammar just to identify the last application of a derivation rule. So when we are going to apply this rule backward, then we practically finish the derivation. So it is the last step going backward from the leaf to the start symbols. And at this point, if we place a dot just before the initial symbol, it means that we are just before something which can be derived from the original initial symbol. So something which can be derived from E. For E we have two grammar rules. That's why we can be just before applying a rule E to T or E to E plus T. So at the beginning of the input, either we have something which can be derived from E plus T or from T, but since at this point we are before just before T, then we can be somewhere before a sequence of symbol which can be derived from T. For example, either something which can be derived from T multiplied by F or T to F. So in this case, we can be somewhere which can be derived from F, which means that it is just before an opening of a pair of braces or just before an ID. So practically we can see that among the non-terminals we could identify that the arithmetic expression should be started either by an ID or the first element of a pair of braces. Okay, and how to calculate the step table? For example, if there is a non-terminal right after a dot, and by reading something can be derived from the X, the dot is placed on the other side, then we can step from one collection to another. So if we have a collection I including such an item where the dot is just before non-terminal X, then the step will lead to a collection of items, which is a closure of all those items where the dot is in the same row but right after the non-terminal X. Okay, and we can go through all the items and check how where we can go by reading certain symbols and generate new sets of items and calculate their closure. And as you will see later on, practically the states of the pushdown automata executing the LR parsing will be assigned to this closure of LR0 items. So for the grammar, what we have introduced with grammar rules E plus T, E to T, T to T multiplied by F, T to F, F to E in braces or ID, and the additional grammar rule where E prime with E prime to E. We have the initial collection of LR items where the dot is just before the initial symbol in the first grammar rule, but its closure includes all the steps where the dot is at the beginning of the right-hand side of the rules applicable to E, and since the dot appears just before T, then the closure includes all the items where the dots are on the right-hand side, in the right-hand sides of the grammar rules applicable to T, and finally, since the dot appears just before F, it appears at the beginning of the right-hand sides of any grammar rule applicable to F. And then when symbol is read and something is read which can be derived from E, then we are going to collect all items where the dot is just before E, place the dot to the other side and apply the operation closure again. But since there is no non-terminal on the right hand side of the dots here, then the LR0 item collection remains the same. It cannot be extended further. Similarly, when something is read which can be derived from T, then we just copy those items where the dot is before the T's and place the dots to the other side. And similarly, if we read F, we just go through this list and we find the only item where F is before the dot. And then go further with the tokens. For example, if the opening bracket is read from the input, then the dot became on the other side. Since this is the only rule where we have this symbol after the dot, so the dot moves to the other side, but it is before the E, so we have to copy all the grammar rules with the dots at the beginning of the right-hand side of the grammar rules applicable to E, and then the dot appears just before T. That's why we have to copy all the grammar rules applicable to T and place a dot at the beginning, and since the dot appears just before F, we have to copy all the items where we have a grammar rule applicable to F and the dot is at the beginning. And similarly, reading a multiplication sign, we got a dot on the other side of the multiplication sign, and since it is before F, we have to place all those items here where a grammar rule is applicable to F and the dot is just at the beginning of the right hand side. And all these lines highlighted by red identifies those LR null items which were generated by the operation closure. And actually the construction of the LR null parsing table is very much similar to an NFA DFA conversion when we had the initial state, which is the set of the states equivalent to the initial state of the non-deterministic finite automata. So we can move from the initial state to, if we can move from one state to another without reading any symbol from the input. So practically on arcs with empty string, then these additional states are included in the set representing the initial state of the deterministic finite automaton. And here we have the LR0 closure of the LR0 items where the dot is just before the initial symbol, but it means that immediately we can jump to any symbol which is at the beginning of the right hand side of a rule, which can be derived from the initial symbol. And similarly, if there is a non-terminal at the beginning of this right hand side, then we can jump to the beginning of the additional rules where which can be derived from that non-terminal and so on. And as you could remember, if we could go from any of these states to another state by reading a certain symbol, then we had to generate the union of the states equivalent to those states where we could go by the red symbol. And similarly, here we have these go-to items, and these go-to items are practically on those closures where the dot are moved to the other side of the certain symbol. That, for example, if we go from the I0 by E, we are looking for those items where the dot is on the other side of the E from those items which were included in the item set I0, and finally we have to generate the closure again. And finally, as you could see, from I0 we can go to I1 by reading E or something derived from E, and to I2 by reading something derived from T, and so on. And for example, at the end, we go to I5 by reading the ID from the initial state. Okay, and then if there is a non-terminal A, and such an item in the collection assigned to the actual state where the dot is just before the non-terminal, then we apply this goto operation to determine the other collection, which can be at the target of this movement by reading a non-terminal. So practically these collections involves all the potential situations where we can have during our procedure reading certain symbols. So if we had multiple choices to read an A, then finally practically we have other multiple choices again where we could have after reading the and these situations are expressed by these LR0 items. And if we have such an item where the dot is at the end, So we have reached the end of something which could be derived from a non-terminal. Then the action can be a reduction from this non-terminal to a sequence alpha for every input symbol which can follow something derived from A. That, for example, if we have something which can follow such a sequence of symbol which could be derived from A, and potentially we have the end of something derived from A, then we can reduce the sequence to A, and then if the same situation appears to the prime version of the initial symbol, it means that we are right after something which can be derived from the initial symbol, so it can be derivated by the grammar. And if in this state at the end of the input we have the $sign, it means that we could generate a sequence of derivations leading to the tokens at the input, and we have reached the end of the input, and in this case the expected operation is accept. And the goto table is defined according to the goto operations for non-terminals, and error messages are assigned to each cell haven't filled in steps 1, 2, and 3. And the initial state is where we have this initial state prime to dot initial state. So even if for the generation of the action table, especially the generation of the reduction rules, we need only the follow sets, but the construction of the follow sets involves the or assumes the availability of the first sets, so we have to construct the first sets and the follow sets similarly as we did at the LLK parsers. The only difference is that in this case the grammar is not the same because we didn't have to eliminate left recursion. And as a result, following the construction algorithm, we can fill in the parsing table by actions like shifts, and as you could see, for example, if you can go from I0 to I4 by reading an opening bracket, and from I0 to $sign to I5 by reading the $sign, then we have a shift operation in this cell assigned to the state 0 and opening bracket, and there is a shift 5 operation assigned to this cell where we are in the state 0 and ID is red. And if we have a collection where the dot is just after the right side of a rule, so at the end of a rule, then if a symbol is at the beginning of the input which can follow a non-terminal, then the action table can involve a reduction rule. So in this case, in state 2, by reading E, we are so when the element of the follow says, for example, this closing bracket is at the input, then this E to T grammar rule is applied backward. And it is the same for all the symbols included in the follow set, so for the dollar sign, the closing bracket, and the plus sign. And state 1 can be achieved only by reading the initial symbol, and if we could read something derivable from the initial symbol and we have reached the end of the input at the same time, then we could generate by the derivation rules all the input, and in this case all the whole input is accepted. Okay, and this is the way how this parsing table is filled in. For example, in the initial state, reading ID, we go to we read the ID and go to state 5. As you could see in the state diagram, from the initial state by ID we go to state 5. And for example, in state 2, for plus sign, a reduction rule is applied. And because this plus is included in the follow set of the non-terminally, as we could see. And for example, as I mentioned in this previous slide, if in state 1 the dollar sign is read, then we are going to accept the whole input. Okay, so during today's lecture, we have seen how to apply a bottom-up parsing table, and by the help of a pushdown automata, how we can parse grammars in this class of languages. And practically, if we start to construct the parsing table and none of the cells involves more than one actions, then this SLR parser is sufficient to derive the derivation rules, how we can construct the parse tree. And the interesting is that in the case of LR parsers, the parse tree is constructed not from the top to the bottom, so from the initial symbol to the leaves, but in the reverse order, from the leaves to the start symbol, and its name is defined as the input is read from left to the right, but in this case the rightmost derivation is executed first, and this defines the order of the grammar rules, how they should be applied to result in the parse tree. And finally, we could see how such a parse tree could be constructed by the introduction of LR0 items, their closure, the go-tos, and then the algorithm which fills in the action table. And for this step we needed the follow sets, which identifies those non-terminals can appear after applying a grammar to a specific non-terminal. And as you could see in a previous lesson, for the LIK grammars, the construction of the follow sets assumes the availability of the first set, so we have to construct the first sets here again. But it was described how to do in the presentation on LLK grammars. Okay, so as a result, we have a new parser which is practically applicable for more languages than the LLK parsers, even if the construction involves more steps, but it is more general. First, we do not have to apply the left recursion, and second, a broader range of languages can be accepted by it. Thank you for your attention.